Alright, good morning. Today we're going to talk about section 6.5, the central limit theorem. Well, before we talk about 6.5, I want to take just a brief look back at what we talked about so far in chapter 6. In 6.2 we talked about the standard normal distribution. And in 6.3 we talked about the book called it Applications of Normal Distribution. Again, I probably would have called this non-standard normal distributions. I think in earlier editions of the book they indeed did call it that, non-standard normal distributions. And in any case, in each of these sections, there were two major topics. Basically, if we were given values, either standard normal or non-standard normal, either z values or x values, where x represented a non-standard normal distribution, we found probabilities. And we did that using the normal CDF command with the usual syntax. And we also worked it in reverse. In other words, given probabilities, typically in terms of an area under a normal distribution curve, we could find the specific values that cut off that area for x or z, whether you're in standard or non-standard cases, and we did these using the inverse norm command with, of course, the TI syntax. Alright, so that's a brief look back at what we did in section 6.2 and 6.3. We're going to go on now to section 6.5, the standard normal distribution. The central limit theorem. Alright, so section 6.5, central limit theorem. It really is central to the study of statistics from this point on. As a motivation, let me again motivate the discussion with an example. Let's say I'm talking about IQ scores. I'm going to let x be a variable that represents all the recorded IQ scores of all time. So let me label that a little informally. X represents all the IQ scores recorded for all time. And someone makes the claim that these IQ scores are normally distributed with a mean of 100. Let me write that down. With a population mean of 100 and a standard deviation, let's say, of 15. Alright, I'm going to give you two scenarios here, A and B. I'm going to need a little more room here, so I'm going to erase this. Remember, we're talking about IQ scores here. Let's look at scenario A here. From this group of IQ scores, I'm going to randomly select one. I'm going to ask then to find the probability that this randomly selected score is greater than 120. So find the probability that a randomly selected IQ score is greater than 120. Okay, that's scenario A. Then I want to talk about scenario B. Instead of randomly selecting one, I'm going to randomly select a group of 20. And I'll ask this question. Well, let me make a little condition here. We'll randomly select 20 and we will compute the sample mean from that group of 20. I'll then I'll say find the probability that the sample mean is greater than the same limit as in part A. Yeah. So in scenario B, I'm asking this question. What's the probability that x bar, a sample mean from a group of 20, is greater than 120? Alright, so part A we know how to do. That's section 6.2. Nothing new there. But I'm going to ask you a question regarding the relative size of part A and part B here. I'm going to say, which probability is greater? The probability you would get from part A or the probability you would get from part B? Alright, you might want to pause and consider this, because this is really central to the study of the central limit theorem. I'll let you pause for a moment. Alright, it turns out the probability in part A should be greater than the probability in part B. Let me discuss why for a moment. The answer to A should be greater. And the rationale is kind of simple. Let me talk about it informally. If the mean is 100 and the standard deviation is 15 for all IQ scores, 120 is certainly above average, is it not? Right? It's 20 points above the mean. And if we take a sample of size 20, we are going to have what I call a dampening effect in this group of 20, and it is more difficult, or less likely we should say, for a sample mean to be in an extreme range or in an above average range. Let me write this down. Answer to part A is greater because it is less likely or less probable for a sample mean to be in what we might call an extreme or even an above average range. I'll put that in quotes. And certainly having an IQ score of greater than 120 is significantly above average. Let me summarize that, maybe using some other words. In other words, there is what I call a dampening effect in a group. And again, you're less likely to be in extreme ranges or even above average ranges when considering a sample mean. All right, so that's really the heart of the central limit theorem. It can give you kind of a visual interpretation of that. Let's talk about this. Consider. Oops, hang on. Consider. Let's take the group of all IQ scores of all time. I'm going to symbolize that with a circle. And I'm going to let x equal all the recorded IQ scores of all time. in millions and millions and millions of individual scores represented by little dots in this big circle that represents the population of all IQ scores. Alright, we claim the distribution of all these X scores, IQ scores, is normal, with a mean of 100 and a standard deviation of 15. Alright, what I'm going to do is plot roughly, very informally, plot the distribution of all these X values or X scores. And we can do that very easily. Basically, I'm going to draw a horizontal axis. This horizontal axis represents all the IQ scores of all time. Well, there's not too many low IQ scores. There's not too many high IQ scores. Most IQ scores land within a neighborhood of the mean of 100. Okay? So this curve here represents the distribution of all these X scores, all these IQ scores. Okay? Alright, now I'm going to ask you to consider another graph here. I'm going to take the same population of IQ scores. Same deal. We've got millions and millions of people taking IQ scores in all of recorded time, and every dot represents an IQ score. Okay? So from the same population, I'm going to take samples of size 20. From the population of X scores, I'm going to take repeated samples of size 20. Okay? So from this population, I'll take a sample of size 20. What I'm going to do is compute the mean, or I'll call the sample mean, and throw them back. Okay? So I'm going to take this sample, compute the sample mean, and I'll have a sample mean. I'm going to call it X bar. Alright, I'll throw that sample back and I'll take another sample. And that's what I mean by repeated. Okay? Now the sample may or may not overlap. Well, from that second sample I'll get another X bar and do it again and again and again. And what I'll have is, in the end, a large population of X bar values. Okay, sample mean values. Alright, so what I'm going to do is plot the distribution of X bar values, much like I plotted the distribution of X values. Alright, what I'll get is this. Well, the horizontal axis here is no longer going to represent X, it's going to represent X bar values. And what's going to happen is, because of that dampening effect in computing the sample mean, it's going to be less likely to be in extreme ranges and more likely to be in the neighborhood of the population mean. Believe it or not, that's supposed to be a bell-shaped curve. Let me try that again. You know, hard to do this freehand on the tablet. I think you get the idea. I may be exaggerating this a little bit. You'll still get a bell-shaped distribution of X bar values, but with much sharper peak, in other words, less of a standard deviation. So these X bar values will still peak at the population mean of 100, but with a much less standard deviation. So I'm going to let the pink curve here be the X bar values, represent the distribution of X bar values. So let me plot the X values on top of this, the original curve of x values might look something like this. Okay? Alright. So this is a visual interpretation of what we said before about that dampening effect. It's more difficult, or certainly less likely, to achieve extreme extremely high or extremely low values when you are considering or computing sample mean values. Okay? Alright, so this is really the heart of the central limit theorem. When you're considering samples, repeated samples of size whatever, you'll have a dampening effect and less of your area under the distribution curve. Alright, so you'll be much less likely to be in extreme ranges when considering sample means. Okay? Alright, so we've given you a kind of an informal, intuitive motivation of a statement of the central limit theorem and a little bit of a visual interpretation. I'm going to go ahead and state it maybe a little more formally now. The central limit theorem says this. It says if x has a normal distribution, in other words, x is a normally distributed random variable with some unspecified mean and standard deviation, the distribution of repeated sample means from that population is also normal, but with less of a standard deviation. Okay? The mean of x bar, right, that's symbolized in our book as mu sub x bar. Right, don't panic, that just means the mean of all these x bar values, the mean of all sample means, is equal to the population mean, the original population mean noted by mu. Okay? The standard deviation of the sample means, well, it's going to be less than the original standard deviation. Remember, the bell is a little sharper, a little narrower when considering sample means. The standard deviation of the sample means is going to be original SD divided by a factor of the square root of n. All right, now the derivation of this very simple formula is beyond the scope of this course, but we certainly will state it for you, and we will use this. Right? It's your original SD divided by the square root of the sample size. Okay, this will be smaller than or less than the original standard deviation. Okay, and that accounts for that sharper bell, narrower bell. Let me get a fresh screen here. And pictorially, we can say it like this, or illustrate it in this fashion. If x is a normal distribution, that means there's not too many high x values, there's not too many low x values. Most are within a neighborhood of the mean of mu. If I, on top of that, plot the distribution of repeated sample means, well, x bar is also normal, also going to be a bell-shaped curve. The mean of the sample means equals the population mean. the standard deviation of the sample means, go back here, the mean of the sample means equals the population mean, and the standard deviation of the sample means, yes, it's going to be original SD divided by the square root of the sample size. In other words, you're going to have a sharper, narrower distribution of sample mean scores. Alright, so of course the yellow curve represents the distribution of X values, and the pink curve represents the distribution of repeated sample mean values. Okay? Alright, let's do some examples. I want to consider that earlier example that I motivated the conversation with. Let's see. Let me go to yellow here. Consider the earlier motivation. We're talking about IQ scores, right? X, a variable that represents all IQ scores of all time. We claim X is normal with a mean of 100 and a standard deviation of 15. Remember, we talked about part A and B. In part A, we randomly select one IQ score, and we wanted to find the probability that X is greater than 120. Alright, nothing new about part A here. I mean, we were able to figure this out as in section 6.3. It's a non-standard normal distribution. Alright, well, that's the equal to the probability that X is greater than 120 and less than positive infinity. And of course, to grind this out, we would use our normal CDF command. Our lower bound would be 120. Our higher bound would be our approximation for infinity, namely 99999. We're in the non-standard case, so I've got to plug in a mean of 100 and a standard deviation of 15. And if I punch this out on my calculator, I get 0.0912. Okay? Now, contrast this with part B. In part B, you may recall we wanted to randomly select 20. And here we want the probability that that sample mean from the group of 20 is greater than 120. Alright, armed with the central limit theorem, now we can compute this as well. Because we know sample means are also normally distributed with a mean that equals the population mean, which is given to us as 100, and the standard deviation of the sample means is your original SD divided by the square root of the sample size. Well, in this case, it's simply 15, right? The original SD is 15, and your sample size is 20. So I have to divide by the square root of 20 to get my new SD. Alright, so I guess in simple strokes, this type of problem is quite the same as part A. Really only one value changes, your standard deviation, right? So the probability that X bar is greater than 120, well, it's the same as the probability that X bar is greater than 120 but less than positive infinity. And of course, I'm going to grind this out with my normal CDF operator. The lower bound will be 120. The higher bound will be our best approximation for infinity. The mean is going to be the same as the original population mean, and your standard deviation is going to be, well, it's going to be new, 15 divided by the square root of 20. Kind of getting crammed up there. Hang on a minute. Let me rewrite this. The lower bound for X bar is going to be 120. The upper bound is going to be our approximation for positive infinity. The original population mean was 100. And the new standard deviation is 15 divided by the square root of 20. Alright, I'm going to go ahead and punch this in just like this on my calculator. And you grind this out, and I get a value of 1.24. I'll call it e minus 9. Of course, that's a number very, very close to 0, so certainly part A, and the answer to part A is greater than the answer to part B as predicted. And if you want to write this in decimal notation instead of scientific notation, it's 124 with 8 zeros between the decimal point and the 1. And certainly part A is greater than part B. It's less likely to be in extreme ranges or even above average ranges when you're talking about sample means. Let me write that down. If I compare, can I get both of these values? If I compare both of these values, let me say that the moral of the story is it's much less likely for a sample mean value to be extreme. Well, either extreme high or extreme low. So part B is certainly much less than the answer to part A. Okay? Alright, let's jump to another example here. I might as well use the same motivating example, as good as any other, I imagine. We'll still stick with the IQ scores here. Consider X is a variable representing all IQ scores, and we know that that distribution is normal with a mean of 100 and a standard deviation of 15. I'm going to consider part A and part B again, much like we did in the last example. And again, in part A, we'll randomly select 1. And in part B, we'll randomly select 20. What's going to change here is the limits of interest here. And part A, I'm going to ask you to find the probability that a randomly selected IQ score is between 90 and 110. And in part B, as you might expect, I'm going to ask you to find the probability that the sample mean is between 90 and 110. So notationally, it's kind of a subtle difference. Instead of an X, we're talking about an X bar. But numerically, these numbers are going to be quite different in our final answer. Alright, of course, in part A, we're going to use our normal CDF command as in section 6.2. Well, here the lower bound is 90. The upper bound for X is 110, not infinity. The mean and standard deviation are given. And if I punch that out, I get a probability of 0.4950. Alright, that was as nothing new there. That's as in section 6.2. Now here in 6.5, or 6.3 I should say. Let me write that down. As in section 6.3. Now in part B, we're going to invoke the central limit theorem here because we are talking about the probability of a sample mean being between limits of interest. The distribution of sample means is normal, just like the population is normal. The mean of all the sample means equals your population mean, which is, of course, given to us as 100. And the standard deviation of the sample means is your original SD divided by the square root of the sample size. And, of course, that's 15 over the square root of 20. Alright, so then I can say this. The probability that X bar is between these limits of interest can be computed with, again, our normal CDF command. Well, the lower limit is the same as part A. The upper limit is the same as in part A. The mean is the same as in part A, but what changes is the standard deviation. Here the standard deviation is 15. Here the standard deviation is 15 divided by the square root of 20. You got a less of a standard deviation. Okay? So I punch this out, and I get 0.9971. Now here the answer to part B is greater than the answer in part A. Now consider this, you're talking about being between 90 and 110, and that is a surrounding neighborhood of the population mean of 100. So I can illustrate this graphically. If I look at my X distribution of IQ scores, it might look something like this. The mean is 100. And this is my distribution for original IQ scores values. If I then draw the distribution of X bar values, well, remember, sample means, if I'm considering sample means, you're less likely to be in extreme ranges, but you're more likely to be within a neighborhood of the mean. So if I consider the limits 90 to 110, I think it's easy to see that more of your available area under that pink distribution is going to be swallowed up between those limits of 90 and 110. Alright, so the answer to part B is greater than the answer to part A because we are talking about limits that are a neighborhood, containing a neighborhood of the population mean. Alright, so let me summarize that. Moral of the story here is sample mean values are more likely to be near the mean, and I should say near the population mean, and of course that means they are similarly less likely to be away from the population mean. Okay, that's really stating the central limit theorem kind of informally. Okay. All right, I want to do an example in the homework list. Let's see, I got enough room here. Let me get a fresh screen. I want to talk about, let's see, no, this one is a worked out example in the book. This is not in the homework list. This is example 2 on page 290. So you might want to pause there and familiarize yourself with that example. So let me turn there, page 290. I'm going to read the example now. Water taxi safety. In the chapter problem, we noted that some passengers died when a water taxi sank in Baltimore's harbor. Men are typically heavier than women and children, so when loading a water taxi, let's assume a worst-case scenario in which all passengers are men. Based on data from National Health, assume that weights of men are normally distributed with a mean of 172 and a standard deviation of 29 pounds. All right, let me write that down. Weights of men. I'm going to let X represent a variable that represents all the weights of all men recorded of all time, and the claim is that these men's weights are normally distributed with a mean of 172 a mean of 172 and a standard deviation of 29. Okay, that's given. Alright, part A. Find the probability that if an individual man is randomly selected, let me reread that. A. Find the probability that if an individual man is randomly selected, his weight will be greater than 175. So, similar to the motivating examples, we'll randomly select one, and I want the probability that a randomly selected man has a weight greater than 175. Alright. And contrast that with part B. Find the probability that 20 randomly selected men will have a mean weight that is greater than 175. So here we randomly select 20 and ask what's the probability that their mean weight is greater than 175. Okay? Alright, in situation A, basically you've got a normal distribution, peaks at the sample mean of 172. Certainly 175 is somewhere above this, and I want the area under that distribution above 175. Alright, this is the probability we seek. So of course I'll get there with the normal CDF command. The lower limit is 175. The upper limit theoretically is infinity. So I'll plug in 6 nines for my approximation for infinity. This is a non-standard case. So I've got to plug in my mean of 172 and my standard deviation of 29. Oh, by the way, that's a 9 up there, 29. And I can punch this out and get a probability of 0.4588. Alright, let's look at part B now. Again, 175 is above the mean, maybe significantly above the mean. So remember, if you're talking about a sample of size 20, it's more difficult or less likely for a sample mean to be in an extreme range or away from the population mean. Alright, so I can grind this out. We know that X bar is normal. The mean of the sample means equals the population mean, that's 175. The standard deviation of the sample means equals your original SD divided by the square root of the sample size. Well, in this case, it's going to be 29 divided by the square root of 20, right? Alright, so this probability can be computed with the normal CDF operator. The lower bound is going to be 175, same as in part A. The upper bound is going to be 9999999, same as in part A. The mean is going to be the same as in part A, 172. But what changes is the standard deviation. It goes from 29 down to 29 over the square root of 20. Less of a standard deviation. Okay? Sharper bell, right? I punch this out, and I get 0.3218, and that is consistent with our claim. It's less likely to be in extreme or above average or even below average ranges when you're talking about means from a sample. Let me write that down. As expected. Probability that a sample mean is, I'll just say it informally, is away from the population mean is less. Okay? certainly this number is less than the answer we got from part A. Alright, let's see, I've got two more examples I want to grind through today. Let's see, this one is from your homework list. This is number 12. Giving you a leg up on the homework. Let's turn there, and I'm going to read the problem here. This is on page 297. It says the lengths of pregnancies are normally distributed with a mean of 268 days and a standard deviation of 15 days. Alright, so let me write this down. X, I'm going to let X be a random variable that represents the lengths of all recorded pregnancies of all time in terms of days. And the claim is that pregnancy lengths are normally distributed with a mean of 268 days and a standard deviation of 15 days. Okay? Alright, they're talking about the effect of diet on the length of pregnancy, so we'll see what they're getting at in a minute. Part A, if one pregnant woman is randomly selected, find the probability that her length of pregnancy is less than 260 days. Alright, so we'll randomly select one pregnancy and ask what's this probability. And similarly, or somewhat similarly, in part B, let me read part B. If 25 women are put on a special diet just before they become pregnant, find the probability that the lengths of pregnancy have a mean less than 260 days. Alright, so again, we're going to get a group of 25, sample size of 25 randomly selected women, and we want the probability that the sample mean is less than 260. And now, again, now note that 260 is away from the population mean of 268. Alright, so you can judge, maybe it's a good idea to think, which answer would be greater, the answer to part A or answer to part B? Well, if we're talking about being away from the mean of 268, well, I'll let you try to chew that out. Alright, I can grind out part A with my normal CDF command. Well, less than 260 means between negative infinity and positive 260. Remember, the population mean is 268 and the population SD is 15. And just like in section 3.6.3, we'll grind this out and get a value of 0.2969. Okay? Alright. In part B, we randomly select 25. Well, again, by the central limit theorem, sample means are normally distributed. The mean of the sample means equals the population mean, which here is 268. The standard deviation of the sample means is going to be your original SD divided by the square root of the sample size. And here that's going to be 15 divided by the square root of 25. Alright, so this can be computed with my normal CDF command. Well, less than 260 means between negative infinity and positive 260, so I'll put those in as my lower and upper bound respectively. The population mean is 268, and what changes here is the SD. Well, of course, 15 over the square root of 25 is 15 over 5. That's really 3. So I suppose you could have computed the SD by inspection. I went ahead and plugged it into the calculator just like that, and I'll get 0.003 0.38. So certainly your answer to part B is less than your answer to part A. Again, you're less likely to be in extreme ranges when you're talking about sample means. That's really what the central limit theorem is all about. All right, one more example here. We'll call it a day. This is also from your homework list. This is number 7B on page 296. All right, we're talking about SAT scores here. I'm going to let X be a variable that represents all SAT scores of all time. All right, for this body of problems, the book tells us that SAT scores are normally distributed with a mean of 1518 and a standard deviation of 325. And I think that sounds reasonable if you've ever taken the SAT exams. All right, now 7B asks us, if 25 SAT scores are randomly selected, find the probability that they have a mean between 1550 and 1575. All right, now notice here, these boundaries for X bar are not well, let's see. If the mean is 1518 and the standard deviation is 325, well, let me illustrate this pictorially. I could claim this. If the mean is 1518 and, well, they want the probability of being between 1550. Notice both of these values are above the mean. And 1575. This may not be to scale, but for demonstration purposes, whoops. For demonstration purposes, I'll shade in the desired probability. Okay, this probability is this area under this distribution between 1550 and 1575. Of course, we'll use our normal CDF command to grind it out. Alright, well, the lower limit is 1550. The upper limit is 1575. The population mean is 1518. And remember, your standard deviation is your original SD, which is 325. But you've got to remember you're talking about a sample mean here, so you have to divide that SD by the square root of the sample size. An easy step to forget. And if I punch this out on my calculator, I get a final return of 0.1210. Alright, so in number 7B, let me check the answer in the book. Yes, 0.1210, okay? Alright, we're approaching the 49-minute mark, kind of a long lecture, but this is an important topic, the central limit theorem. So I'll leave you to review the text and the homework assignment, and of course complete the online exam. Alright, this concludes section 6.5, Central Limit Theorem.